So in today's lesson, we're going to take a lot of the stuff we've learned in this unit and put it all together. So we've talked about different types of energies, we've talked about work, right? And we've even talked about energy transformations from one form to another. Okay, so any object can possess maybe just kinetic energy, or maybe just gravitational potential energy, or maybe a combination of both. Okay, we call this mechanical energy. Okay, so I have a couple examples. Say a hockey puck sliding on a flat ice, that has only kinetic energy. Right? It has motion, but it's not increasing its height. An acorn hanging from a tree has only gravitational potential. So again, it has height, but no motion. Okay, whereas a parachutist that's falling, well, they're falling, they have motion, so they have kinetic energy, and they also have gravitational potential energy because they're at some height above the ground. Okay, now the work energy principle says that the net work acting on an object changes your kinetic energy. Okay, this says mechanical energy. Okay, and when I say network, is we talked a lot about work that was being done, and let me just grab a textbook. Okay, so first example, if I lift this up, I'm applying a force up, its displacement is up, so I am doing positive work. But gravity is down even though displacement is up. So gravity is actually doing negative work. Okay? And if I'm lifting it up at a constant velocity, if you remember from the forces unit, all of our forces are in equilibrium, therefore my applied force equals the force of gravity. And since the forces are equal, the work being done is the same as well. It's just one is positive and one is negative. So your net work would be 0 in this case. But according to this equation, that makes sense because net work is change in kinetic energy. So if our motion isn't changing, then net work should be 0. However, if I were to take this put it here, and push it, initially, my applied force is greater than the force of kinetic friction. So I'm able to accelerate it. Right? I'm doing more positive work than kinetic friction is doing negative work. So my net force, sorry, not my net force, my net work is positive, its kinetic energy is increasing. Okay, so a net positive work increases kinetic energy. But once I stop pushing, the only force acting on it was, well, horizontally anyways, was friction. So the only work being done on it was negative, and it came to a stop. So a net negative work removes kinetic energy from whatever system we're talking about here. Okay, so work can either, or network can either remove or give energy to a system. Now work can give different types of energy, not just kinetic energy. So if we're being specific about the type of work we're talking about, like say the work I'm doing on this book, if we're just talking about the work that I'm doing on this book, well, that work is positive, but in this case I'm not giving it kinetic energy, I'm giving it gravitational potential energy. Okay, if I let go, gravity does work on it. In that case, gravity does positive work because the force of gravity is down, its displacement is down, right? And in this case, it's actually gravity is giving it kinetic energy. Okay, so different works can give different energies. Different works can take away energy. But the network either gives or removes kinetic energy. Let me just pause it there because I know I've been speaking. All right, so we've also talked about energy transformations. One of the examples I gave was a microwave. You plug in a microwave, so you start with electrical energy. That microwave creates, well, microwaves, microwave radiation, which which is radiant energy. That causes water molecules to vibrate. That vibrating is, well, by definition, increasing the temperature and therefore creating thermal energy. So energy is going from one form to another form. Okay? Now I said before we drew these little diagrams with dots in it, and I said it's very important you always keep the number of dots before and after a transformation the same, no matter what energies you put them to. So if we were to move forward and not use dots but actual numbers, right, we could say, for example, maybe we started with 100 joules of electrical energy, and then we got 95 joules of thermal energy and 5 joules of radiant energy. It's still extremely important that the total amount of joules or energy we have on one side of the equation is the same as on the other side of the equation. Why? Because this is the law of conservation of energy. Okay? And it says that the total amount of energy in a system is conserved. You cannot create energy out of nothing. Okay? And of course, existing energy cannot disappear. So we're going to use this idea, this law of conservation of energy, to do some problems. But first, let's look at an example of what I mean. Here we have a diver. Okay? Diver's up here, 10 meters above the ground. It's not moving yet. So all of its energy is gravitational. Doesn't have any kinetic, so you can calculate that total mechanical energy to be 6.4 kilojoules in this case. Okay, and this is a case where I did the calculations here. Someone who is 65 kilograms. Alright. Then, sometime later, that person has fallen halfway to the pool. Now you can easily calculate gravitational potential energy because we know the person's mass and the person's height. And we know they're on Earth as well. So we know gravitational potential. Kinetic energy you can calculate using our equations of motion. Okay. So there are equations of motion. We can figure out, okay, what's the acceleration and so on. We actually know the acceleration because it's in a gravitational field. We can calculate what speed they'll be going at that point. Knowing the speed, you can calculate the kinetic energy. Because kinetic energy is 1/2 mv squared. If you add the two to find the total mechanical energy, you get 6.4. That was the exact same as up here, 6.4. Okay? And you can continue doing this all the way to the bottom, where at the bottom we have only kinetic energy, but still that total energy equals 6.4. Okay, so as the diver is going from the top, his energy is being converted from gravitational to kinetic, but that total amount of energy remains constant. Okay, so let's go try some problems. Our first problem says, a 56 kilogram diver jumps off the end of a 7.5 meter high platform with an initial horizontal speed of 3.6 meters per second. Okay, so let's just draw what's happening to get an idea of what's going on. So here we have a platform with a diver. Okay, that platform is 7.5 meters high. And jumps off with an initial speed of 3.6 meters per second. Now the good news is, because energies are all scalar, we don't really care what direction that initial speed is. Doesn't matter. Okay, oh, it says horizontal. Still doesn't matter. Part A says determine the diver's total mechanical energy at the end of the platform relative to the surface of water. So right here, we need to figure out the total energy that is available. So let's start by just saying the total energy is equal to all our kinetic energy plus all of our gravitational potential energy. Now you can calculate kinetic separately and gravitational separately and add them together, but I like punching a whole bunch of things into my calculator at once, so we're just going to do it together. So this means that our kinetic energy, we'll write our equation, 1/2 mv squared, plus our gravitational, mgh. Now if you like math and you want to factor out that mass to make it easier, you can. I won't do that with you. Let's just focus on the physics. Okay. And we're going to put in our numbers now. So 1/2. Our mass is 56. Our initial velocity is 3.6. Don't forget to square it. Plus mgh, so mass again, 56, times g, which is 9.8, times our height, which was 7.5 meters. Okay, if you plug all that into your calculator, you'll get a total energy of 4,479 joules. Okay, we'll just pause there. So part B says, apply the law of conservation of energy to determine the diver's speed upon reaching the water. So I've got some water down here. The diver is going to jump down. Now right here, right at the top, total energy is 4,479 joules. Right here, it's 4,479 joules. Here, 4,479 joules. 4,479 joules, 4,479 joules. That total energy doesn't change. So if the total energy at the bottom is 4,479 joules, we can also say that the only energy present at the bottom is kinetic. And the reason why we can say that is because when our person is here, they are at our reference level, which we said that's where the height is going to be 0. So there's no gravitational potential here. All the energy is kinetic. So we know that that total amount of energy, 4,479 joules, must be equal to all of our kinetic energy, which is 1/2 mv squared. And that there is no gravitational at that point. So with that concept in mind, we can actually figure out what the speed of this person is when they hit the water. All we just need to do is rearrange the equation a bit. If we multiply both sides by 2 and divide by m, we get 2 times 4,479 joules. It's a terrible 9. All divided by, so divide both sides by mass, which is 56, equals v squared. And then, of course, we'd have to take the square root of both sides to get what v is. And you should get v, if you try this on a calculator, and make sure you try it, is 12.6 meters per second. I did it quickly there because I saw I was running out of room. So question 2 says, a 0.20 ball, that's trying to say 0.20 kilogram ball, is thrown straight up from the edge of a 30-meter tall building at a velocity of 22 meters per second. Okay, let's draw that. It's always important to draw what's happening so you get an understanding, a more visual understanding. So here we have a building. Okay, it is 30 meters tall. Okay, and we have a ball that initially we're going to throw up at 22 meters per second. And it says the ball moves up to a maximum height and then falls to the ground. So it's going to go up and then all the way back Use the law of conservation of energy to answer the following questions. Okay. What is the total energy of the ball at the start? So right here. So right there, we need to ask ourselves then, right here, what energies are present? Well, we have height, right? This is our reference point. So we're at a distance of 30 meters above the ground. So we have gravitational potential energy. We also have speed. It's being thrown at 22 meters per second, so we have kinetic energy. So our total energy at this point is the sum of those gravitational and kinetic energies. So we just need to plug in the equations for both, put in all the numbers, and see what it ends up to on our calculators. So gravitational potential is mgh, kinetic is 1/2 mv squared, and now we sub in our numbers. So mass is 0.2. I'm going to run out of room, so I'm going to be bad and not write units here. 9.8 times our height is 30, plus 1/2 mass 0.2 times a velocity of 22, and don't forget to square. Okay, so when you plug in all of that information, you'll get about 107.2 joules. Left a couple extra significant digits because we're not done. All right, so part B says, what's the maximum height of the ball? So the maximum height comes here. And as we talked about when I paused the video, right here, when the ball changes direction from going up to going down, at some point, the instant it changes direction, its speed is 0. And if its speed of 0, it has no kinetic energy. So up here, all of the energy is gravitational. So for part B, we can say all of our energy, all of this 107.2 joules, equals gravitational potential energy, which is mgh. And we can solve now for h by dividing both sides by mg. Okay, so h, these cancel on the right, is 107.2 joules over the mass, 0.2, and I'm leaving out units again because I'm running out of room, times gravity, 9.8. Okay, so we get our height to be 54.7 meters. Okay, now part C says, what's the speed when it hits the ground? Okay, so again, when it hits the ground, the speed is not 0. We're talking about that instant. Okay? And so at that instant, it is moving with some speed, but it's also at a height of 0. So there's no gravitational potential here. The only energy we have there is kinetic energy. So now all of this energy has now been converted into just kinetic energy. So we can say all of that 107.2 joules is now kinetic energy, which is 1/2 mv squared. We can rearrange and solve for speed. Really running out of room now. I multiply both sides by 2 and divide by m. Take the square root, and you get the square root of 2 times 107.2 joules divided by the mass, 0.2 kilograms, and we get a speed of 32.7 meters per second. All right, question 3. You have many roller coasters have loops where carts roll on a track that curves sharply up into the air. In the roller coaster shown, the cart must have a minimum speed of 10 meters per second at the top of the loop to make it around safely. So it means right here, we need at least a speed of 10 meters per second in order to make it around safely. Assuming that the roller coaster starts from rest at the top of the first hill, so right here, its velocity is 0, starting from rest. And there's no friction, so we're not going to lose any energy to heat or anything like that. What is the minimum height of the first hill to ensure success? So basically, how high does this need to be able to just make it around that loop? Okay, so now we have to think of energies. Let's call this point A and this point B. Due to conservation of energy, we can say all of our energy at point A must equal all of our energy at point B. Conservation of energy. No energy is lost, no energy is created. They must be the same. All right, well now we need to think of, all right, what energies are at point A and what energies are at point B. Now really we've only talked about and calculated 2 types of energies, gravitational and kinetic. Now here at point A, the speed is 0, so there is no kinetic. The only energies we have here are gravitational. So we have gravitational at A. Okay, if you want to write kinetic at A, that's fine, but just remember that it's going to be 0. And that must equal all the energies at B. Now at B we have a certain height and we have a certain speed. So we have gravitational at B and we have kinetic at B. So this is the equation that we need to use to actually calculate. So now we're going to put in our formulas for gravitational. So mgh, but I'm going to specify this is the height at A. Okay, because I'm going to be using h over here as well, and I don't want to get them confused because they are different h's. This is the height here. This one is going to be the height here, which I will label as HB. Now the mass and gravitational field strength are going to be the same, so I don't need to label those. And then I have the kinetic energy at B, so 1/2 mv squared. I can write VB squared, but I don't have VA anywhere in here because it's 0, so I'm not going to bother. And what we're solving for is the height at A. So I know M. Actually, I don't know M, but that's okay because I have an M in every single term. So if I divide every single term by M, it is going to just cancel, which is good. You don't want to be on a roller coaster where the mass is that important. Otherwise, the lineups can be extremely long trying to get the mass right every time they run the ride. Okay, so we have G, which is 9.8, times the height of A, equals, again, here we have G, 9.8, times the height at B, which I know is 16, plus 1/2 times v squared, that's this one, so times 10 squared. Okay, and then what I can do is divide both sides by 9.8. The entire thing, remember, don't just divide one term or another term by 9.8. Just like up here, we had to divide every term by mass. We will get a height of 21.1 meters.